Okay, today we're going to pick up where we left off. Last time we talked about acid ionization constant Ka. We said that was a specialized type of equilibrium constant that in that expression, acid ionization constant expression, there must be the hydrogen ion or the hydronium ion present in the expression for it to be called a Ka. So today, what we're going to do is we're going to focus on Kb, and then we're going to work from Kb. Show you how that works with acids or bases, and then we'll look at both Kas and Kbs. So last time Ka, this time Kb, and then we'll go from there. All right. So most bases that we're going to work with in real life are weak bases. So the general form for a weak base is that you have B for base reacts with water. According to Bronsted definition, water will act as an acid, donate a hydrogen ion to the base. We get Hb positive here, and then that generates the hydroxide ion. And again, water is a pure liquid, so we don't see it in the expression. It's integrated into the equilibrium constant itself, the um, base constant. And so you have your concentration of your products divided by the reactant, just like we had in chapter 15. But again, the key is the hydroxide ion has to be present in the expression if you're going to call it a Kb. So now we have in our repertoire, we have K at concentration, we have K at pressure, we have Kw, the ion product constant of water, we have Ka, acid ionization constant, and Kb, the basicity constant. And we're going to add to that before we get through this whole thing about equilibrium. So there's five of them that we need to know. What do they mean? What's their definition? What's their expression look like? All these are going to be very important as we progress through the chapter. So here's some examples of weak bases, and notice most of these are a kind of a covalent compound. These are not a metal hydroxide. These are all you would generally consider these as organic compounds. And so we have ethylamine, methylamine, and the thing I want you to get, what I want you to think about here is when you see the word amine, it is derived from ammonia. All right. So what we're doing here, if you look at this, we're knocking off one of the hydrogens off of the ammonia, and then we're attaching. It's called an alkyl group to it, and so we replace a hydrogen with an alkyl group. In this case, the ethyl group. So that's why this is called ethylamine. This is methylamine. Then we have ammonia, and then here we have attached a cyclical structure to the nitrogen, and so this is called pyridine. So just keep that in mind. Again, notice these basicity constants are all very small. Um, they're all less than one, and that tells us that the molecular base is preferred over the ionized base of the ionized base that has the hydroxide ion on the product side. So again, let me just show that again up here. So what we're saying is that if I take ammonia and I react that with water, that I get the ammonium ion positive, and then I get the hydroxide ion. And this reaction is reversible. But again, because this is such a small Kb value, it tells us that at equilibrium, the molecular base is much more prevalent than the ammonium ion and hydroxide ion, the products. And how do you know that? Again, when you write the equilibrium expression for this, it would be Kb equals the concentration of the ammonium ion times the hydroxide ion concentration divided by the molecular ammonia. And for this number to be that small, it means this the numerator has to be small and the denominator has to be large to make a number less than 1. So that's what you ought to be thinking, is that this ratio being less than 1 is going to tell you that the reactants are the predominant species at equilibrium. And so here's some other examples. Aniline. So here, aniline, the thing that's important about aniline is it looks just like ammonia, except we now have replaced the one of the hydrogens with a benzene ring here. And then urea, if you're thinking about major in biology, this is a super important one. So this is what urea looks like. You may want to categorize that. And look how small the KB is for it, 1.5 times 10 to the negative 14th. So urea mainly stays as this molecule when mixed with water. It does not dissolve very well or become ionized, let's say that. So solving problems with weak bases, going to look just like weak acids. The differences, we're going to be looking at hydroxide ion concentration versus hydronium ion concentration. So let's look at our first problem. This is an ice table. By the time we get finished with this, you're going to be sick of ice tables, but you should know them backwards and forwards. It shouldn't be hard to do here. So what do? It says, what is the pH of a 0.040 molar ammonia solution? So again, the first thing you must do when you're doing a problem like this is you have to have a balanced chemical equation. So that's what we have. Ammonia aqueous in water forms the ammonium ion and the hydroxide ion. Yes, we see that it's reversible. And so we write the expression for this. Always write the expression to see who the players are. Notice water is not in the expression because it's a pure liquid. Pure liquids are integrated into the equilibrium constant, or in this case the basicity constant or base ionization constant, because as long as there's some water present, its concentration is not changing appreciably. So we have initially ammonia, we have 0 of the ammonium ion and the hydroxide ion. So again, real quick, Q is less than K. Always do that step. I can't stress that enough. If I plug in the values, this is 0, this is 0, and this is 0.04, the value of Q is going to be equal to 0. And the equilibrium constant, or the basicity constant, is 1.8 times 10 to the negative 5th. So therefore, Q is less than K. Just real quickly. Why is that important? Because that tells you which direction this way. This reaction is going in this direction to the products to the right. And it's all 1-to-1-to-1 ratios again. So it's minus X of this plus X of the two products, like so. And here's my equilibrium concentrations. So again, ice tables, that's what they're called. Ice tables, initial change, equilibrium. We plug that into the expression, and we get X over 0.04 minus X equals 1 times 10 to the negative 5th. This is 4 times 10 to the negative 2. It's about a 10 to the third difference. So we're going to assume that this X is negligible. All right. So assume the X is negligible. And then we'll check to see if that's a good assumption as we move through. But first thing we want to do is just assume the X is negligible. Makes it easier for us. All right. So assuming this X is negligible, then we have X squared over 0.040, and we have X squared equals 1.8 times 10 to the negative 5th times the concentration. And then we take the square root to get X by itself, and we get 8.25 times 10 to the negative 4th. All right, so here's how you're going to tell if that was a good assumption. To assume this X is negligible, what we're going to do is take the amount of hydroxide ion formed divided by the original concentration of the base, multiply by 100%. If this percent is less than 5, then this approximation is okay. Okay? So if this number is less than 5, by making this approximation that this X is negligible, then we're fine. And if that's the case, if this is less than 5, then I'm going to take the hydroxide ion concentration, plug it into here, and what do I have here? If you said pH, you're incorrect. We took the negative log of the hydroxide ion concentration. This is the pOH. Now, to get the pH, you would say 14.00 minus 3.07, and that would leave you 11, oops, no, that's not going to work, 10.93, 10.93, all right? So make sure that you, this is on multiple choice exam and quiz. I will have that number, and if you say that's your pH, that tells me you're not understanding where this comes from. All right, tells me you don't know that you're solving for the hydroxide ion concentration. So here we solve for the pOH. We subtract that from 14 to get the pH. So make sure you do that correctly. And read the question carefully, because sometimes I do ask for just pOH. Sometimes I want to know what the pOH is. Sometimes I want to know what the pH is. You've got to read the question carefully. And so there we go. 14 minus 3.07 is equal to 10.93. Not hard. Same process as Ka. It's just that this is a Kb. How do you know it's a Kb? It's got the hydroxide ion concentration in the expression. And we're looking at basicity constants or base ionization constants. We're not looking at Kas. We're looking at Kbs in a table. So that's another reason. All right. So the next type of problem is we can use pH to determine the Ka of a weak acid. Well, we can also use it to determine the Kb of a weak base. So this is kind of the reverse process. And again, these are common on the exams because they're quicker, easier to solve. We definitely don't get into a quadratic here. So just keep that in mind that you need to be able to do this problem quickly. All right, so here we have caffeine, the stimulant in coffee and tea, is a weak base, and it ionizes the water according to the equation. So what I want you to get out of this, you're looking at that caffeine and you're going, oh, this looks complicated. Look how big that molecule is and so forth. All you're doing here is, if you want to solve this quickly and you don't want to write this all down, just put a B here. And there's the water. And so now we have BH plus because we've added a hydrogen ion has donated to the caffeine. And then what we have left is the hydroxide ion. And then the Kb is equal to the BH plus the hydroxide ion, or times the hydroxide ion concentration divided by the base. Okay, you can do it that way if you want to. If you want to simplify it to make you get through the question quicker. All right, here's the parts you've got to have in order to do this problem. What was the initial concentration of the caffeine? And what's the pH of the caffeine? Okay, they're asking you to determine the base ionization constant. Okay, so tell me what your plan of action is. You've got your balanced chemical equation. You must have that in order to do any equilibrium problem. That's number one. Number two is you have the expression, and you know this is a Kb because the hydroxide ion is in the expression. And then you go, do I know what the hydroxide ion concentration is? You know what the pH is. If you know the pH, you can determine the pOH. And if you know the pOH, you can determine the hydroxide ion concentration. So there's my plan of action for that. So the next thing is to develop an ice table. So the ice table grounds you, says this is what I need to find, and so forth. So let's do that. So here's my ice table. So in my ice table, I have the caffeine. And again, if you don't want to write this all out, don't. But here it is. The caffeine reacts with the water, forms the protonated caffeine and the hydroxide ion. So initially we have 0.15 molar of the caffeine. We don't worry about the water. It's constant. We have 0 of the protonated caffeine and the hydroxide ion. So again, real quick. Q is less than K. You know the reaction is going to go in the forward direction. And so the difference here of saying minus X, and plus X is you're asked not to solve for the equilibrium concentrations. You're asked to solve for Kb. So these have to be known. There's no minus X or plus X. So here's what we do. We talked about that the pH was 8.45 was the pH. All right, I'm going to subtract that from 14. And if I do that, I get 5 and 5 and 13 minus 8, 5. So that's my pOH. And then I know that if I want to know what the hydroxide ion concentration is, I raise 10 to the negative pOH. And that's going to be 10 raised to the negative, they didn't show that right there, but there's your answer right there. 10 raised to the negative 5.55. Okay? And you get this number here. So that could be confusing on this slide. You do this, but then you got to plug it in here. All right? So that is the hydroxide ion concentration at equilibrium. That means that's also the concentration of the protonated caffeine. And we did know that's how much of this the caffeine we lost. It's just like minus X, plus X, plus X, but we know what the X is. So here are my equilibrium values for the caffeine, the protonated caffeine, and the hydroxide ion. I plug those into this equation. I'm going to get 2.82 times 10 to the negative 6 squared, just that times that, divided by 0.15 minus, which is what we have. And you say, that's the same as this. Yeah, look, notice how much it's changing. This doesn't even register to the hundredths place. All right? And we get, our answer is 5.3 times 10 to the negative 11. So here we solve for the Kb. Much easier problem. We don't have to worry about quadratic, and that's the advantage of doing solving for the basicity constant versus solving for equilibrium concentrations. So I hope between seeing the values for Ka and solving for pH or solving for Ka, and then seeing Kb and solving for the hydroxide ion concentration or the pOH or the pH, and then solving for the basicity constant that we're doing here, that you've seen enough examples that you should be able to do the problems that's in your assignment, and also if you need some additional practice, the ones in the back of the book. The thing I would say, I'm just cautioning you that you want to work proficiently with this. Quizzes are timed, exams are timed, and you want to not dwell on it. You want to move through the process fairly quickly. And the main thing is to come up with that plan of action, write your ICE table, and go from there. Because really, this stuff up here doesn't take that long. It's just recognizing it. I mean, just like I did here, that didn't take that long to get this, which then gives me this. But if you don't know what you're doing, you may spend 5 minutes on it. So assignments where you practice, but when you take the quiz, you're supposed to be proficient enough to actually do it. All right, so the next slide is we want to look at the strength of Kas and Kbs. So the strength of a conjugate acid or base, the relationship between Ka and Kb of a conjugate acid-base pair. And you go, why do I need to know about this? This is setting us up for the next chapter, which is on buffers, and buffers are used a lot in biology. We use buffers to keep the pool water at a certain pH. We use buffers to keep a solution at a certain pH so our planaria and other microorganisms can thrive. Or maybe you have a fish aquarium and you've got to keep the pH at a certain pH for the fish. And so we're going to start looking at the strength of conjugate acid-base pairs. And that's going to give us an idea of what we're going to use this for is to determine when I put a salt in water, is the salt going to be acidic or basic? So it's important important section, and it carries over into the next chapter. So let's look at this first one here. The first one shows us that this reaction goes in the forward direction only, because this is a strong acid. This is not reversible. It goes only one direction. And so this reaction, if I take the chloride ion, the conjugate base, and I put that in water, it's not going to form hydrochloric acid and hydroxide ion. That reaction does not happen. And we're glad it doesn't, because think about it. You sprinkle table salt on your soup, and table salt dissolves into a sodium ion and a chloride ion. If the chloride ion did react with water, you'd form a molecular acid plus a strong base, and it would burn your tongue. This reaction doesn't happen. The reason why this reaction doesn't happen is because this is such a weak conjugate base that even in the presence of the hydronium ion, which there's a typo here, it should be a plus up here, this reaction doesn't go this way. It doesn't happen. So even if I take this weak conjugate base and put it in pure water, this reaction still doesn't happen. So this is showing the example of the stronger the acid, the weaker the conjugate base. And hydrochloric acid being a very, very strong acid, the conjugate base is very, very weak, and this reaction, and the conjugate base cannot even accept a hydrogen ion from water. So that's going to be really important, because you can see right now, table salt has no effect on pH as far as the chloride ion goes. Well, let's think about the sodium ion. Is the sodium ion going to react with water and form NaOH plus the hydrogen ion released? Because that's what would be happening. Well, that doesn't happen either. The sodium ion is not going to accept a hydroxide ion from water and form a strong base plus the hydrogen ion. So that reaction doesn't happen. So what we know is table salt, sodium chloride, is a neutral salt. It doesn't affect the pH. And again, the reason why is because the conjugate acid of sodium hydroxide and the conjugate base of the hydrochloric acid will not react with water and form a strong base or a strong acid. That's not going to happen. Leaving us with, if this happened, it would be an acidic solution. If this happened, a basic solution. All right, so now let's look at a weak acid. So weak acid, we've talked about, it's not one of the 7 strong ones, is hydrofluoric acid. So hydrofluoric acid, a weak acid, when we pair it with water, yes, the water will donate a proton to the hydrofluoric acid, the molecular hydrofluoric acid. We form the hydronium ion and the conjugate base, the fluoride ion. So this is a weak acid. I'll just say WA. The weaker the acid, the stronger the conjugate base. So this is a fairly strong conjugate base, since this is a weak acid. So if I take the conjugate base and add it to water, yes, it will accept a hydrogen ion from the water, form the molecular acid, and generate the hydroxide ion. So the pH actually goes up. You're thinking it's a weak acid, I should have a pH that's low, but because the fluoride ion, now this is a separate reaction here, but if I just take the fluoride ion and add it to water, it's actually going to have a pH greater than 7, above 7, because the fluoride ion does accept a hydrogen ion from the water and forms a hydroxide ion, which makes it pH greater than 7 and makes it a basic solution. So again, what we're learning here is the weaker the acid, the stronger the conjugate base. When I take the conjugate base and I add it to water, I'm going to generate the hydroxide ion and make a basic solution. So you're going, why do I need to know this? Okay, so one of the substances we use to fluoridate drinking water is sodium fluoride. So this is the chemical formula for sodium fluoride salt. So it's water soluble. If you don't know that it's water soluble, you probably need to go back and look at your solubility rules. It's in a table in chapter 4, I believe. And so this dissolves into water as sodium ions, aqueous, and fluoride ions, aqueous. Well, we just saw that sodium is not going to react with water and form sodium hydroxide and hydrogen ions. That is not going to happen. Why? Because that's a strong base. This is a very weak conjugate acid. Not going to happen. But the fluoride ion, we just saw fluoride does react with water and forms the weak acid, hydrofluoric acid, because it's a weak molecular acid, plus the hydroxide ion, aqueous. So it makes a basic solution. So when we put sodium fluoride in water, it is going to make a basic solution, a pH greater than 7. Sodium has nothing to do with it. So that's where we're going with this. You're going to have to look at a salt based on the Kas and Kbs of the weak acid or the weak base. Determine if the salt is going to be an acidic salt, a neutral salt, or a basic salt. And you say, why do I need to know this? Because this has to be mastered in order to talk about buffers in the next chapter. All right, next slide just shows you that if it's a strong acid, the conjugate base is so weak it doesn't react. So again, the nitrate ion is not going to react with water and accept the hydrogen ion from the water and form nitric acid plus the hydroxide ion. That is not going to happen. But cyanide, this is a weak acid. It's not one of the 7 strong ones. So if I take the cyanide ion and I add that to water, then water is going to donate a hydrogen ion to the cyanide ion. We're going to form hydrocyanic acid, the molecular form, plus the hydroxide ion. And so the solution is going to be basic. All right. So, it's a classic example like you've heard of, maybe like in a spy movie, somebody swallows potassium cyanide to kill themselves or whatever. If you take too much cyanide, it generates too much hydroxide ion in the stomach, and it generally causes the person to throw up, and they may not actually ingest enough cyanide or get it into the bloodstream to actually kill them. So this will irritate the stomach lining, causing a gag reflex. So just keep that in mind, that the cyanide is hydrocyanic acid is a weak acid. That makes this a fairly strong conjugate base, which allows it to accept a hydrogen ion from water and form the weak molecular acid and generate the hydroxide ion. All right, so let's look at bases. So a strong base, something like sodium hydroxide, goes 100% to these 2 ions, dissociates. So this is the conjugate acid. It's not going to, sodium is no way going to react with water and accept the hydroxide ion and form sodium hydroxide plus the hydrogen ion. That is not going to happen. Okay. So ammonia is a weak base. If I add it to water, it's going to accept the hydrogen ion, and we're going to get the ammonium ion plus the hydroxide ion. This reaction is reversible. So if I take the ammonia ion and I add that to water, it is going to donate. All right, so the conjugate acid of ammonia is the ammonium ion. So the ammonium ion, since it's a fairly strong conjugate acid, because ammonia is a weak base, the strong conjugate acid will donate a hydrogen ion to water and form the hydronium ion plus ammonia. The generation of this hydronium ion makes the solution acidic. So where you see this in everyday life is like if you work on a farm and you're fertilizing your lawn with ammonium, or fertilizing your farm with ammonium nitrate, the nitrate is not going to react with water and form the acid plus the hydroxide ion. And you go, how do you know that? Because this is a strong acid. This reaction does not happen. This is a very weak conjugate base of a strong acid. But the ammonium ion is the conjugate acid of the weak base ammonia. And so when we add that to water, yes, this will donate a hydrogen ion to the water, form the hydronium ion plus ammonia. So it actually acidifies the soil. So that's why you'll see people after they fertilize with ammonium nitrate, later on they'll put quicklime or something like that to sweeten the soil, to get rid of that, to reduce the acidity. So that's why this is important. It's used in agriculture. It's used in different processes, especially plastics and things like that, where you have to look at the conjugate acids and the conjugate bases to see how it affects the pH. So right here, it is important to recognize that the words strong and weak do not mean the same thing in context of conjugate acids and conjugate bases, as they do in the context of acids and bases in general. A strong conjugate reacts with water, either accepting a proton or donating a proton. So if you hear the word strong with conjugate, it is going to react with water, and that is going to change the pH of the solution. So a strong conjugate acid acts as a weak Bronsted acid, and a strong conjugate base acts as a weak Bronsted base in water. A weak conjugate does not react with water to any measurable extent, like, for example, the nitrate that we just did. So for nitrate, again, where does nitrate come from? It comes from the strong acid nitric acid, and the nitric acid goes 100% to this. So this is a weak conjugate base. There's no way that's going to react with water and form a strong acid plus the hydroxide ion. That's not going to happen. It's important that it doesn't happen, because if it did, I mean, we'd have problems. Nitrate would actually make a basic solution, and it would be, we wouldn't be expecting that. So again, this is the weak conjugate base of nitric acid. Does not happen. All right, so let's look at the relationship between Ka and Kb. There's a typo here. So here we have recognize the acid. When you're doing this, get your naming down, because I find students just don't remember the name. So this is acetic acid, and there should be a double arrow here. It is a reversible process. So here we have acetic acid. It will donate a hydrogen ion to the water and form the hydronium ion. And then what's left over is the conjugate base, the acetate ion. And again, this reaction goes nowhere near 100% to completion. All right? It's not acetic acid is not one of the strong 7 acids. So we write the Ka for this reaction. So then if I take this conjugate base and I add it to water, it's going to, this is the conjugate base of a weak acid, this weak acid up here. So yes, the conjugate base will react with water. Water will donate a hydrogen ion to the conjugate base, form the molecular acid and the hydroxide ion. So because the hydroxide ions generated, that would make a basic solution. So this is a Kb. Why is it a Kb? A basicity expression, a base ionization constant expression, because the hydroxide ion is present in the expression. Just like this is a Ka up here because the hydronium ion concentration is present in the expression. So when you have something like this, you go, well, which one's going to dominate? Which one is going to determine the overall pH of the solution? Well, when we add the two together, the two reactions together, this is what happens. And again, these are all double-headed arrows here. We get two waters become hydronium ion and hydroxide ion. Okay? Because these cancel out, and this is what we have left. Same thing in general. Any acid that we add to water that's a weak acid is going to go through this process, and the conjugate base is going to go through this process. And notice we get the same outcome. So which one's going to dominate? Which one of these species is going to dominate in the end is going to determine the pH of our solution. If the hydronium ion dominates, then it's going to be an acidic solution. If the hydroxide ion dominates, then it's going to be a basic solution. How do we know which one's going to dominate? Because we know what the Ka of this reaction is, the acid ionization constant, and we know what the base ionization constant is. Whichever one of those is larger is going to dominate the reaction. Same thing with bases. So with bases, let's look at the general equation for bases here. You have a base reacts with water, and this again is a weak base. Protons donated or hydrogen ions donated to the base, we get Hb positive, and the hydroxide ions generated. This is a Kb, right? And then if I take the conjugate acid of the base and I add that to water, yes, this will happen as well. If this is a weak base, which it is, then this is a fairly strong conjugate acid. And so this reaction happens, and that generates the hydronium ion. So again, notice we get the same equation. Whether it's Ka or Kb, it's two waters form a hydronium ion and a hydroxide ion. So here's what we know. This is really important. You need to memorize this. This is another tool you're going to be using. When you multiply Ka times Kb, you get Kw. And you know Kw has to equal 1.0 times 10 to the negative 14th at 25 degrees Celsius. So know that equation. You are going to be using this equation to convert Kas to Kbs through Kw. All right, so let's look at a problem here. So it says determine the Kb of the acetate ion, determine the Ka of methyl ammonium ion, the Kb for the fluoride ion, and the Ka for the ammonium ion. So to do all of these problems, the tool that you're going to need is Ka times Kb equals Kw. So for the first one, A, we're going to use this equation. We're asked to find the Kb. So the Kw for water is 1 times 10 to the negative 14th. The Ka, so we don't have a Ka for this acid here. This is not an acid. This is the conjugate base of the weak acid, acetic acid. All right, so if I had a hydrogen on it here, you would have the weak acid. So what I need to do is find the Ka for the weak acid. And I know what that one is. It comes up so much. It's 1.8 times 10 to the negative 5th. So that's how we're going to solve them. We're going to use one of these two equations to solve every one of these problems here. All right, so then the question is, where do I get this number? Where do I get 1.8 times 10 to the negative 5th? Well, you get that from a table, and we've seen the tables already in this chapter. or probably on a on a quiz problem or test problem, it's located within the problem itself. So this has to be garnered from a table, and you're looking for the Ka for acetic acid. So we're looking for the Kb for the acetate ion. That's what we're trying to solve for. But it's Kw divided by Ka, and you need the Ka for this acid. And again, the acid, before we get the conjugate base here, is this. All right, so then the next one is, you have this conjugate acid. What did that come from? Well, it came from the base methylamine, right? Came from this substance. So you have to look up the Kb for this base. When it accepts a hydrogen ion, it becomes this. That's the conjugate acid. So the Ka for this acid is going to be equal to Kw divided by the Kb for this base, which you look up in a table. All right, let's do the next one. Conjugate acid is, so we have HF, right? And hydrofluoric acid becomes the fluoride ion. They want to know what the conjugate, the Kb for the fluoride ion is. So I look up, so I have 1 times 10 to the negative 14th, Kw, and I look up the Ka for the acid, HF, hydrofluoric acid, because if I add a hydrogen ion to the fluoride ion, then I get this. And so when I look that up, I get 7.1 times 10 to the negative 4th. 1 times 10 to the negative 14th, Kw, divided by Ka for hydrofluoric acid gives me 1.4 times 10 to the negative 11th. Same thing on this last one here. We know that the ammonium ion comes from ammonia. And so I need to look up the Kb for ammonia. There it is. Here's the Kw. So Kw divided by Kb gives me the Ka for the acid, for the ammonium ion, the acid here, the conjugate acid. All right. This is actually a typo here. This shouldn't be acid, this should be base. Let's see that now. Because fluoride ion is the conjugate base, and we have to go back to the acid. Just like here, this is the conjugate acid, we got to go back to the base. So there's a typo on that acid there. All right. Let's go on. Diprotic and polyprotic acids. So what does that mean? It means that there's more than one hydrogen to give in an acid. And so we're looking at something like carbonic acid. So carbonic acid, you know, is a weak acid, so it's reversible. We lose a hydrogen ion to the water. It's a Bronsted definition. We get the hydronium ion, and then what's left over is the bicarbonate or hydrogen carbonate ion. So that's Ka1. The bicarbonate ion can then donate a proton to the or hydrogen ion to the water, and we form again the hydronium ion. And let me just say, this is much weaker than this. This is a stronger acid. Even though it's a weak acid, it's still stronger than the bicarbonate ion. Why is that? Well, this has got a negative charge. Does it really want to lose another hydrogen ion to the water and form the carbonate ion and make it a 2 negative charge? Not likely. So this Ka2 is going to be much less than Ka1. All right? So this is easier, but still this is going to be less than 1 because it's a weak acid. And this is even a weaker acid. So there's Ka2. So this is called a diprotic acid. It has 2 hydrogens to give, diprotic, diproton. And so there's 2 protons in carbonic acid that can be released. Here's the first release of 1 proton. Here's the next release. So let's look at some diprotic and polyprotic acids. So sulfuric acid, you know, is a strong acid. And the reason why it's a strong acid is the first Ka is very large, much, much larger than 1. They don't even have a number here. They just say it's very large. I mean, we're talking hundreds probably. That's one of these protons popping off. Then we have the hydrogen sulfate ion, HSO4 negative. And we're going to lose this hydrogen, and that's going to leave us with sulfate 2 negative and the loss of another hydrogen. Its Ka is less than 1. That tells us that this reaction is reversible. It's not going one direction. That it mainly stays in this form, and some of it changes to that form because this Ka is less than 1. Again, if you're unsure, draw your expression. So Ka2 would be the concentration of the sulfate ion times the concentration of the hydrogen ion divided by HSO4 negative. So for this number to be less than 1, the denominator has to be larger than the product of the numerator. So that tells us it mainly stays in this form and does not ionize to hydrogen ion and sulfate ion. So oxalic acid, you see there's 2 protons, 2 hydrogen ions on the end. That gives you an indication this is an acid and it has 2 acidic hydrogens to give. So the first one comes off, and it's a weak acid to begin with. It's not one of the 7 strong acids. So it's 6.5 times 10 to the negative 2 for the acid ionization constant. When we go to remove the second one, it's going to be even harder to remove because this now is a negative ion after we lose this one. And it's 6.1 times 10 to the negative 5th. Sulfurous acid, it's a weak acid to begin with. So when we lose the first hydrogen, it's 1.3 times 10 to the negative 2 for the acid ionization constant, which is less than 1. Again, compare these two right here. Strong acid up here, weak acid down here, Ka less than 1 here. So to remove this second one, that's really going to be difficult. 6.3 times 10 to the negative 8th. Not likely to happen. I mean, it does happen, but it's not rare compared to the HSO3 negative. Scorbic acid, again, diprotic. Got 2 hydrogens to give, one here, one here. And so first one comes off at 8, first Ka1, 8.0 times 10 to the negative 5th. To remove the second one, 1.6 times 10 to the negative 12. So diprotic acids. We can get into polyprotic. And so polyprotic acids, again, when we have more than 2, like phosphoric acid, you got 3 acidic hydrogens. First Ka, 7.5 times 10 to the negative 3. Still a weak acid to begin with, not greater than 1. Second one comes off, 6.2 times 10 to the negative 8. Third one comes off, 4.8 times 10 to the negative 13. So what I want you to get out of this, every time we take a hydrogen ion off something, the likelihood of that reaction going to completion for the next one is much less. And you can see that in these Ka values. All right, so again, let's look at this one again real quickly. So what you have here is you have phosphoric acid. It's a weak acid. It loses a hydrogen ion, and then what we have left is a dihydrogen phosphate ion. Now, you guys taking biology, this is an important one. That's why I'm pointing it out here. They call it tribasic, dibasic. So then the next one is we take the conjugate base, H2PO4 negative, and we lose another hydrogen ion, and we get the hydrogen phosphate ion. And now it's a 2 negative ion. Doesn't really want to lose that last hydrogen. But we could take that conjugate base, HPO4 2 negative, and it loses another hydrogen ion, and then we get the phosphate ion by itself with the 3 negative charge. But see how the Ka for that is 4.8 times 10 to the negative 13. That it tells us all these Kas are less than 1. Just tells us these are the dominant species. This being this is not likely to form that because it's such a small Ka there. It does form a little bit, I guess, but not much. So this is the type of problem you could have with a diprotic acid. So you got oxalic acid, a poisonous substance used mainly as a bleaching agent. Calculate the concentrations of all species present at equilibrium when a 0.10 molar solution at 25 degrees Celsius. All right, so the first Ka, the loss of one hydrogen ion from here to form that is 6.5 times 10 to the negative 2. We take the conjugate base, we add that to water, loses its second hydrogen ion, it's 6.1 times 10 to the negative 5th. So how do we solve for this problem? Well, it's an ice table again. We've been doing ice tables. We're going to keep doing them. So the only difference here is you've got two ice tables. You're going to do dual ice tables here. So for the first one, you have the original concentration of the oxalic acid. These are 0. Q is less than K. Reaction goes in a forward direction. We're going to lose X amount of the oxalic acid. We're going to gain X amount of the hydronium ion. We're going to gain X amount of the hydrogen oxalate ion. Then we're going to do a second ice table. We take the hydrogen oxalate ion, add it to water. We get the hydronium ion plus the oxalate ion. Now, we don't know what this is yet, but we know that we can solve the first one. We can get X, then we can plug that into this, and then we're going to form X amount of this to combine with X amount of this. That's why it stays X, and this is 0. So even in this second equation, second ice table, we know that Q is going to be less than K because we have a 0 here. So we know this reaction is going in the forward direction as well. So look at the first ice table and set up the equilibrium expression. Hydronium ion concentration times the hydrogen oxalate ion divided by the original acid. So the Ka is so small. We're going to assume this X, look at that, look at this. We're going to assume this X is negligible. We're going to solve for X. We get 8.1 times 10 to the negative 2. We put in 8.1 times 10 to the negative 2 divided by 0.1. We get a percent ionization of 81%. You go, oh, what does that mean? Remember, if it's 5% or greater, you can't do the approximation. You can't do the approximation. Again, if your ionization is 5% or greater, then you can't do the approximation. This is 81%. Based on, and you could tell that was going to happen because this is 1 times 10 to the negative 1, and this is 6.5 times 10 to the negative 2. There's not a big enough separation there. So what does that mean? You're going to have to do quadratic equation. So the quadratic equation ends up being this: x squared 6.5 times 10 to the negative 2 minus 6.5 times 10 to the negative 3 equals 0. Here's my A is equal to 1, B is equal to this number, and C is equal to this number. Plug it in the quadratic, solve for x, you get this number. Plug this into your first ice table, and now you have the equilibrium concentrations of the products in the reactant. So now we're on to the second ice table. So the second ice table, you have what we just solved for, that the ion, the hydrogen oxalate ion, is 0.054. We know that this is 0.054. We know this is 0. We know this is going in the forward direction because, again, Q is less than K. We're going to lose Y amount of that. We're going to gain Y amount of this and Y amount of that. We plug that into this equation. Now, we're going to make some approximations here. We're going to assume this X is negligible, or this Y is negligible compared to that concentration. This Y cannot be canceled out because any change from 0 to Y is significant. And we're going to assume that this Y is negligible compared to the concentration. Oh, this makes it real easy, right? Because now what you have is you have Y times 0.054 divided by 0.054. Those cancel out. And Y equals the acid ionization constant for the second reaction. All right, so let's see if that approximation holds. So we plug that in and we get this. And if I take the Y is the amount of hydrogen ion, and I divide it by the original concentration of the acid, then I get 0.11% ionized. That's less than 5%, so the approximation holds. And now I'll go back and plug that into the ice table to figure out what my concentrations are. Works really well. It's just that this is a hard problem because it's 2 steps, 2 ice tables combined, and we had the FOIL method in there. That makes it difficult. So to get the A, B, and C coefficients to plug into the quadratic equation. All right, that's where we're going to stop at with this. The next part will finish chapter 15.